Welcome to solverfy.
In this problem, we're going to talk about Gauss's law and the electric potential. So first, about Gauss's law, we need to remember that let's say that we have a charge distribution whose total charge is equal to Q, and that we draw, let's say that we draw a surface, a Gaussian surface around this charge. Then Gauss's law tells us that the electric flux, defined as the surface integral of the electric field times the element of area, is equal to the total charge enclosed by the surface divided by epsilon zero. Okay. Um, Also, we have that the electric potential V is equal to minus the integral of the electric field dot dr from the point. Actually, let me write this as V minus V0. This is the potential difference between R0 and R. Okay, so now we can go on to our exercise. What we need to do is to consider a, a sphere, a non-conducting sphere that has a radius r0. So let's say that here is our sphere. And this sphere has a uniform density such that the total charge of the sphere is Q. And our goal is to find what is the value of the potential energy first in question A when R is greater than R0. Well, in that case, the we can use Gauss's law in order to find the electric field, and then with that we can find the electric potential. The first thing we need to notice is that when V goes to infinity, when R goes to infinity, we want V to go to zero. Okay, so that's something that we're gonna impose over our equations. So first, notice that since there is spherical symmetry in our system, then the electric flux is just, let's say that we draw the surface at a distance r from the center. The electric flux is just the electric field at that point. Notice that all throughout the surface, the electric field is the same, times the area, which is 4 pi r squared. And this is Q, that's the charge enclosed by the surface, divided by epsilon zero. So the electric field is Q over 4 pi epsilon 0 r squared. Now V is minus the integral of uh, the electric field, dr. And what I'm going to do is to integrate from infinity to 0. Okay, because at infinity, V is equal to 0. So V is equal to minus Q over 4 pi epsilon 0 r, and there is a minus here. So there's so there's an overall positive sign. So V is Q over 4 pi epsilon 0 r. Notice that when r goes to infinity, V goes to infinity as we want to. Then we want to find what is the value when r is smaller than r0. Here, we're going to need to impose that the electric potential must always be continuous. So the electric potential at R, the electric potential at R is greater than R0. When calculated at, let's say, R is equal to R0 plus, this means that it's equal to R0 from outside of the conducting sphere, this is equal to V of R is equal to R0 minus. Okay, so first, I'm gonna draw here our surface. So now we have that R0, this is here is R0. Our surface, the distance between the center and our surface is R. So what we have is that the electric field times the area element is equal again to E times 4 pi r squared, and this is equal to the enclosed charge. I'm going to call it lowercase q divided by epsilon 0. Now notice that lowercase q is equal to the density times the volume of 4 pi r squared r cubed over 3, and rho, the density, is the total charge divided by 4 pi r0 cubed over 3, then multiply by 4 pi over 3 r cubed. So this is just q r cubed over r0 cubed. So E times 4 pi r squared is equal to q r cubed over r0 cubed. So E is equal to q r cubed over 4, and actually there is an epsilon 0 here. So 4 pi epsilon 0 uh, r0 cubed, and we have to divide everything by r squared, so I'm just gonna cancel the 3 here. So this is the electric field. Now the difference V minus V0 is equal to uh, actually let me just write V. I'm gonna write V as minus the integral of E dr, and then I'm gonna leave it as an indefinite integral, so I'm gonna sum a term in the end. So V is equal to minus the integral of qr over 4 pi epsilon 0 r0 squared dr. So this is minus qr squared over 8 pi epsilon 0 r0 squared. Okay, there is a plus a certain constant here. I'm going to call it k. Okay, and now we have to impose that v is continuous. So v for r slightly greater than r0 is, let's say, v at r0 plus, that is equal to q over 4 pi epsilon 0 r0 squared, and this is minus q r0 squared. Actually, there is a small mistake here. It should be r0 cubed here. Sorry for that. And here as well. So q r0 cubed over 8 pi epsilon 0 r0 cubed plus k. So these terms here cancel out. And we are left with k. I'll notice that this is 2, 8. So k is equal to 3q over 8 pi epsilon 0 r0 squared. Actually, there's no square. It should be just r0. Okay. So v is equal to minus q r squared over 8 pi epsilon 0 r0 cubed plus 3q over 8 pi epsilon 0 r0. I'm gonna write it as um I'm gonna write this as q over 8 pi epsilon 0 r0 times 3 minus r squared over r0 squared. Then finally in question D, we have to plot v and e as a function of r. So see, let's start with v. Notice that v for r smaller than r0 is this value here. So it's a parabola, but decreasing one until it reaches the value. So it starts with 3q over 8 pi I0, I'm sorry, epsilon 0 r0, and this, and finally it becomes q over 8 pi I0 r0, and it decays like this, initially as a parabola, till it reaches r0. Let me write this a little better. And then it starts decaying as 1 over r. Okay, this is v as a function of r, and then we can draw e as a function of r as well. Okay, so notice that e from here starts at 0 and increases linearly until it reaches the value of q over 4 pi epsilon 0 r0 squared. Okay, so it starts at this point, does something like this till it reaches r0. So it's equal to q over 4 pi epsilon 0 r0 squared, and then it decays as 1 over r squared. Okay, which is the answer to our exercise.